Now let's just make a short review of some properties of the hydrogen atom. Then we can see how the eigenstates would be modified by various corrections. Now, if you write the differential equation, the Schrödinger equation, plus minus e squared over 4 pi epsilon 0, 1 over r squared, no, 1 over r, psi is equal to e psi. So this is the Schrödinger equation for the hydrogen atom. Now let's look at the units of certain quantities. What is the unit of h bar squared over 2m? This is one parameter that appears in the differential equation. The solutions will depend on this parameter.
Times.
Well, Laplacian has the dimension of 1 over meters length squared, 1 over meter squared. So this whole thing should have the units of energy. So it is the unit of h bar squared over 2m will be joule meter squared. What's the unit of e squared over 4 pi epsilon 0? Well, like joule times meter. The ratio? So h bar squared over 2m multiplied by 4 pi epsilon 0 over e squared this has the units of meter. And this h bar squared over m 4 pi epsilon 0 over e squared is what we usually call the Bohr radius. I don't think we include that too. I mean,
it should be something like that.
well, this is the only possible quantity with the dimension of mass, of meters. Without using the, without using E, without the 2. Now, of course, usually we don't use this combination. Let's see. What's the unit of h bar c? Well, h bar has units joule seconds, c has units meters per second, so it is joule meters. This is the unit of e squared over 4 pi epsilon 0. So if you just take the ratio, it's a dimensionless quantity, which we call the fine structure constant. And its numerical value is 1 over 137 approximately. This is just the definition.
Is the dimension analysis work all the time like that?
Quite disappointingly, yes.
Why disappointing?
I mean, you do all those pages of calculations, and at the end of the day, what you obtain is some number close to 1. You see, I mean, if you use meters to describe the hydrogen atom, I mean, that's useless. I mean, the hydrogen atom doesn't care about the mass, about the meter, sorry. The natural length unit for the hydrogen atom is the Bohr radius. Now, if you write everything in terms of Bohr radius, the average of r to the n will be the Bohr radius to the power n. It will be proportional to this one. Of course, there will be some proportionality constant, which will typically be around 1. And you do pages of calculation to calculate that number. If you just want, for example, to check the convergence, it's enough for you to have the order of magnitude estimate. And for the order of magnitude estimate, dimensional analysis almost always works. Now this, okay, I said that you can write the Bohr radius in just one line. This is more than one line. Let's write it down in just one line. I will use this definition of alpha. Let's see. It's the radius of the electron, right? So it has to be somehow related with the mass of the electron. So if there is a mass of the electron, we can write down a characteristic momentum, just using constants of nature. So to obtain something that has the dimension of the momentum, what should I multiply it with? C. Well, if you have a momentum, then you can write a characteristic wavelength, which will be h bar over mc. This is called the Compton wavelength. This is kind of the maximum you can compress the electron wave function. Well, in the equation for the hydrogen atom, C doesn't appear. So we somehow have to get rid of the C. Alpha has 1 over C. So if I multiply C by alpha, then there's no C appearing anywhere. And alpha is dimensionless. I can just multiply, divide, and the dimension doesn't change. This is the Bohr radius. Okay, now this is the one-line derivation. I just copied the first line to the second line. That doesn't count. Okay, any questions on this? Yes?
If you like to define structure constant, you said, if you're not used to some terminology, you can ask him. I don't know where it appears.
The fine structure constant. Yeah. Well, it will appear in the fine structure of the spectrum, which we will discuss now. It's just a constant for the time being. We will see that it just describes how the wave energy levels of the hydrogen atom, they are split. So what are the energy values of the hydrogen atom? En. Well, it's something like E0 over n squared. E0 is some, in fact, let's write it down. It is something like 13.6 electron volts over n squared. And E0. Do you remember the expression of E0? So let's just do some classical physics. If you remember, let's just assume a circular orbit in the 1 over r potential. So you would probably remember that the kinetic energy is minus 1/2 the potential energy. Derive it. So this is equal to minus v over 2. This is classically. V is minus alpha times C over r squared, r times 1 over 2. Alpha C is E squared over 4 pi. Let's also put the H bar. H bar C alpha over R. Well, since we are writing the E0, let's just put the minus sign is on the previous line already. So this is plus, this is plus, this is 2, the Bohr radius. Now this would be my first guess for E0. Just from dimensional arguments, from, I don't know, the potential energy, from the classical circular orbit. Let's see, I never remember the exact expression, so let me just cheat a bit. So this is m over 3 h bar squared e squared over 4 pi epsilon 0. E0 is equal to m over 3 h bar squared e over 4 pi epsilon 0, right? E over 4 pi epsilon 0, everything squared. This should, let's just compare. Now, our guess was h bar c alpha over 2, while the Bohr radius was h bar over m alpha mc. So this is h bar. Now h bars, they just cancel, right? mc squared alpha squared over 2, right? Yes. So let's look at this expression over there. Does units match? Yes. M squared c squared alpha cubed alpha squared over 3. Now e squared over 4 pi epsilon 0 is alpha h bar c, alpha times h bar c. So that's where I have the c squared. That's why the h bar squares cancel. Well, I'm off by a factor of 1/2. Not bad. I mean, I'm sure after this you will remember to correct for the factor of 2 and change it to 3. So now let's look at some corrections to the initial Hamiltonian. We have this Hamiltonian over here, which we obtain by starting from the energy expression p squared over 2m plus v of r. Now p squared over 2m is the non-relativistic kinetic energy. But it's possible that the electron might be rotating quite fast, so we should be adding relativistic corrections to it. Now the exact relativistic kinetic energy is square root of p squared c squared plus m squared c to the 4 minus mc squared. So the square root is the Einstein's energy relation, and mc squared is the rest mass. The rest is the kinetic energy. So are you familiar with this one? Now the non-relativistic limit is the limit when Pc over mc squared is much less than 1, or P over mc. This is the non-relativistic limit. Now, we know that the solutions of the Schrödinger equation work relatively well, so at least we know that the corrections should be small. So if the corrections are small, the electron is quite non-relativistic, so we can just take the first correction to the non-relativistic kinetic energy. And for that, what we can do is the square root of p squared c squared plus m squared c to the 4. This is equal to mc squared times 1 plus p over mc squared, all of it raised to the power 1/2. Well, that second term is the correction, is a small term, so I can just use a Taylor expansion. So this is equal to mc squared 1 plus 1/2 p squared over mc squared plus no, there's no p squared, right? Plus 1/2 times minus 1/2 times P over MC squared, all of it squared divided by 1/2, plus the remaining terms. Now you see there is this plus 1 over here, which just gives me MC squared, and there is this minus MC squared over here, so they will just cancel each other. So the kinetic energy would be 1 over 2 MC squared times P over MC squared plus MC squared times minus 1 over 8 P over MC to the power 4. This is the first correction. And if you just open the parentheses, etc., you get P squared over 2M. This is the non-relativistic kinetic energy. Minus, we have this correction over there, P to the 4 divided by M cubed C squared 8. So now we have H is equal to H0 minus P to the 4 divided by 8 M cubed C squared. So this is our H prime. These are the operators. This is the first non-relativistic correction. Now, let's see. We will be using the power perturbation theory. First of all, is there a degeneracy or not in the hydrogen atom? Now, for the H0, you see, in perturbation theory, what we do is we just start with H0. Is H0 degenerate? You see, in the hydrogen atom wave functions, we have the 3 quantum numbers, N, L, and M. We don't have spin yet. There's nothing in the Hamiltonian that depends on the spin yet. We will add those. H0 doesn't contain the spin, but there's neither H prime contains the spin, so forget about the spin for the time being.
It's not spin dependent, so
Well, let's see. H0 acting on my wave function would give me the energy of my wave function, but the energy of my wave function depends only on N. L and M, they are degenerate. I have N squared degeneracy at the state N. There are N squared states that have the same energy. So these are all 0. For example, the ground state is not degenerate. There is a single one. Well, if you look at the first excited state, then the angular momentum can be 0 or 1. And there are 3 states with angular momentum 1, and there is the ground state. So these are not the ground state. There is also one more state with angular momentum 0 in the first excited state. And these 4 states, they all have the same energy. If you go to the second excited state, that is N is equal to 3, in that case, there are 9 states that have the same energy. Okay, so we have to look at the degenerate perturbation theory. Or maybe not. So let's look at this one, H prime. Does H prime commute with L squared? You see, this is our H prime. It is momentum to the power 4. Well, you see, you can think of it as the P squared. I mean, you should think of it as P squared. P squared itself commutes with L squared. So P to the 4 also commutes with L squared. Now let's look at this one. H prime, L squared, N L M, N prime, L prime, M prime. This should be 0 because the commutator itself is 0. So this is equal to N prime, L prime, M prime, H prime. Well, L squared acting on that state gives me H bar squared L plus 1 minus, well now L squared is on the left, so I can act it on the bra. And that would give me N prime, L prime, M prime, H bar squared L prime plus 1 times H prime and L M. Or I can just cancel the H squares on both sides, and I have L prime plus 1 minus L plus 1 N prime, L prime, M prime, H prime, and L M. This should be equal to 0. So if L is not equal to L prime, N prime, L prime, M prime, H prime, and L M, this is equal to 0. So H prime is already diagonal. So it doesn't mix states with different L. States with different L, even if N and N prime are equal, then those are degenerate states. But if L and L prime are different, H prime doesn't mix them. The corresponding off-diagonal elements are 0. Let's see. So we just looked at one thing. H prime and LZ. So does it commute? Well, everything is scalar in the Hamiltonian. There is no angular thing. So this is 0. So we just do the same thing. And that tells us M prime minus M, N prime, L prime, M prime, H prime, and L M. This should be equal to 0. Well, it means N prime, L prime, M prime, H prime, and L M. This is equal to 0 if M is different from M prime. So these two expressions basically mean that in the degenerate subspace, H prime is already diagonal. So remember, if there is degeneracy, what we had to do is we had to diagonalize H prime in the degenerate subspace. But in this subspace, it's already diagonal. Now this is in fact a general property. So if you see what we had used over here, there is H prime, but there is another quantity which commutes with H prime. So we can use the eigenstates of that other quantity, in this case it was Lz and L squared, to choose our basis states. And once we choose the basis states using those other operators, H prime is already diagonal. So we don't need to worry about this degeneracy over here. So let's look at in general. Okay, let's assume N and M are degenerate states. So in principle, we have to deal with degenerate perturbation theory. And also assume there exists an operator let's say O such that H prime and O commute. If O of n is, let's say, mu n, and O of m is equal to mu m, that is, these degenerate states are also eigenstates of the O operator with different eigenvalues, then H prime m and is equal to 0 if mu m is different than mu n. So this is the general statement of our previous relation, what we had done over here. So in the previous case, we have two operators. We had the L squared and Lz. It commutes with the Hamiltonian. And different degenerate states, they differ by the eigenvalues of L squared and Lz. And hence, their corresponding matrix elements of H prime is 0 if we have different states. So we don't need to worry about degenerate perturbation theory. So if we don't need to worry about degenerate perturbation theory, the first correction to the energy of the state NLM would be just NLM H prime NLM. NLM, well, H prime we had calculated, it was minus p to the 4 divided by 8 m cubed c squared. NLM. Well, the book does this derivation, which I don't like. P to the 4. So this is the derivation of the book. So what it says is we already know that P squared acting on NLM, this is equal to 2m times E minus V NLM. So P to the 4 NLM NLM, this is equal to NLM 2m E minus V squared NLM. Do you see what is wrong here? P does not commute with V. So it assumes that P commutes with V. Not even in one dimension. In one dimension, V depend. I mean, as long as V depends on the position, P will not commute with it. Anyway, it gives the correct answer. Well, the only alternative I have is just to write the P to the 4 and take the matrix elements. We know the eigenstate, so evaluate. Which is, well, it might make a good homework, but I don't know if you will learn anything from that. We just have to write the wave function, take its fourth derivative, take its Laplacian, and then once more take the Laplacian and see what it brings, but it won't be illuminating, let's say. Let's stick with this derivation. So if you buy this argument, then NLM H prime NLM, this is equal to minus 1 over 8 m cubed c squared. We have 4 m squared. Let me not write the NLMs all the time. E squared minus 2e, the matrix element of V, plus the matrix element of V squared in this NLM state. We see this cancels this one. This will cancel with this one, leaving a factor of 2. This is equal to minus 1 over 2 c squared e squared minus 2e times e squared over 4 pi epsilon 0. Well, v has a minus sign, minus e squared over 4 pi epsilon 0. The average of 1 over r plus minus e squared over 4 pi epsilon 0 times the average of 1 over r squared. Well, then of course you have to calculate these values of 1 over r squared, put it over here, do all those integrals. I will just write the result. I will just check the result here.
Can you use the approximation routine?
Well, we can. Let's see what it will give. I mean, the problem is, the thing that I cannot drive is 1 over r squared. Yes, there is 1m. Right. 2m. Well, this 1 over r squared is something like 1 over ab squared. That is what we would naively expect on dimensional arguments only, but there is also L plus 1 over 2 over here. I mean, that L plus 1 over 2, you have to calculate. 1 over r, I think it was 1 over ab, straight 1 over n ab or something like that, n squared ab. I mean, this 1 over n squared, you cannot predict from dimensional arguments. And this, now this angular dependence is one thing that I want, because basically before, whatever the value of L, the energy was independent of the value of L. But now we have a correction which depends on the value of L. So we are kind of lifting the degeneracy somehow, partially at least lifting the degeneracy. Now L equal to 0 state is no longer degenerate with L equal to 1, which is no longer degenerate with L equal to 2, or etc. Now before they were all degenerate. But even the relativistic correction will just give you a correction, a term that is that lifts this degeneracy. Now another thing to note is that, okay, so if you just put 1 over, the average of V will also be proportional to E itself. So you see the V squared, the expectation of V squared will also be proportional to E squared. All of these terms are proportional to E squared. So the change in the energy of the NLM state, the first correction, will be proportional to the energy of that state squared divided by MC squared, with some factors containing L or 2's, etc. There's 2 over here, these factors of L over there. And so if you look at the fractional correction, this will be approximately E and L are the energy of the state divided by MC squared. Well, the energy of the state is 10 electron volts. For the electron, MC squared is 500 kilo electron volt. That is 5 times 10 to the power 5 electron volts. So this ratio is of the order of 10 to the power minus 5, the correction. So if you are planning to measure this correction, you have to be able to measure the energy up to a level of 0.1 per mil. So if you can make such a precise measurements, then you can detect this shift. Or you can directly try to look at this splitting, which might be easier to measure. Because instead of one line in the spectrum, you should be seeing 2 lines, two very closely spaced lines. At least for, not two, but for the first excited state, 2 lines, for the second excited state, 3 lines, etc. How many depends on how many different values of L you have. Each one will now have a different energy. Now, any questions? Have you heard of Runge lens vector? Check it. You might have heard it in classical electrodynamics. No, not in classical mechanics, sorry. In classical mechanics.
Yeah.
Well, that's the vector that points from the focals to the point of closest approach. Well, the interesting thing about this one is that it's conserved. Well, you see, whenever you have a conserved quantity, you have the corresponding degeneracy. For example, since angular momentum is conserved, you have rotational invariance. Different m values should be degenerate. Different values of m should be degenerate. Here we lift the degeneracy corresponding to different L values, but we are not yet lifting the degeneracy corresponding to different m values, because it's due to the rotational symmetry. Rotational symmetry forbids any non-degeneracy for different m values, at least at this level. But there is no, without using this vector, there is no reason why different L vectors should be degenerate, different L numbers. There is no symmetry that causes that. And indeed, if you just add any correction, it will lift the degeneracy between different L values. We had seen one example. Now, the reason why for the hydrogen atom different L values are degenerate is because this is also a conserved quantity. It commutes with your Hamiltonian. Anyway, so questions? They are waiting for us outside.